Good morning, dear students. Welcome to another session of microwave and antenna. So in previous session, we started off our discussion pertaining to point sources. In which we discussed few of the concepts and we solved few of the problems related to point sources. And using a radiation pattern, how do we go ahead with identification of directivity? So these were the aspects what we discussed, that is based on the pattern what is given for the source. Using the total power theorem, we have identified what is the directivity for a given antenna pattern. So that we have discussed in a previous session. So these were a few things what we have come across. So we discussed how do we get these kind of patterns also. So next we will be discussing regarding another parameter, that is two isotropic point sources. So we'll be discussing regarding those aspects. So which is actually array of point sources. So in array of point sources, we'll start off our discussion with respect to considering two isotropic point sources. So in previous session, we discussed regarding what is point sources, how do we identify with help of this, what is the directivity and other aspects. Now in these cases, right, what we'll be doing is we'll try to identify what is the pattern, how the pattern will appear when I consider two point sources. So it is the array of 2 point sources conditions. So let us have a look at these things now. So now we'll be discussing regarding array of point sources, in which we'll be first considering 2 point sources, isotropic point sources, and then we'll try to see what is the pattern associated with these point sources. Now remember, isotropic point sources is the ideal condition what we are looking out for. So based on that assumption, we try to see what will be the pattern if we have two isotropic point sources for a given condition. So based on that, what is the pattern we'll be having? So in this case, so in this case, so we have to consider two isotropic point sources. So we'll be considering source 1 and source 2 to be isotropic point sources, which are separated by a distance d between them. The distance between source 1 and source 2 is d. Next, what I have to do is, because of these 2 point sources, how the field variation will be. That is what I have to look out for. Now, when I'm specifying that, I need to specify some conditions. So what is the first condition we'll be looking out? We'll be looking out for the first case in which we have two isotropic point sources which have same amplitude and same phase. So both are in phase with respect to each other. The first condition is the source 1 and source 2, what we are considering, are having same amplitude, are having same amplitude, and both are in phase, both are in phase with each other. So that is the first two conditions what we are looking out for. Next, the distance between source 1 and source 2 is considered to be the value d. The distance between these two sources is d. Now, based on this, now we need to identify what is the total field which is due to these two sources together. What is the total field which is due to the two sources which are presented together? Now, for this, what we do is we consider an observation plane. We consider an observation plane which is at a distance r from the origin, which is at a distance r from the origin. So when I'm considering this observation point, in this case, what we are doing is we are considering the midway between these two sources. The distance between these two is d. The midway is half of this distance. So this one we will be considering as the reference point to measure the field at a observation plane. So in this case, we are considering the midway between these two sources as the reference point. So in your coordinate system, when you have the coordinate system, you have the origin. So this is the reference point to measure all the values on the coordinates. So this is how I can just give the implication of this reference point. So with respect to this point, I'll be measuring what is the field E1, what is the field E2, and due to this, what is the overall field at the distance r. So now in this case, source 1, source 2 are two isotropic point sources. Distance between them is 2. The midway between those is considered as the reference point, with respect to which I'll be trying to measure what is the total field at this point due to source 1 and source 2. So with respect to this origin point or the reference point at a distance r, we consider the plane of observation. We consider the plane of observation. Now with respect to this, what is the field due to this and what is the field due to this? So that parameter we need to identify. So before going into that depth, we'll see what are these values, because this will be helpful in our estimation. So with respect to this point, if I just consider the distance between source 1 and source 2 is d. Therefore, the distance between source 1 and this reference point or the origin is d by 2. And similarly, distance between this reference and the source 2 is d by 2. So this is your physical distance with respect to the reference point. Now, if I happen to measure the angular distance, since what we are doing is we are considering an observation plane at this point, and if I assume that if there is an element over here, if it radiates a field, it will be say radiating the field in this direction, and at a distance r, I am trying to measure the value. At present, I don't have any source. If I consider, this is how it will be. So this field, if I consider from this origin point, right? If I consider the field from this origin point, this will be the reference field. So the phase of this one will be 0. The phase of this one will be 0. Now, since I am having only two sources over here, that is source 1 and source 2. So I'll be having fields due to these two parameters, these two sources. So I need to identify what is the field due to this. In order to identify, I need to measure the angular variation, that is angular distance. So d by 2 is the physical distance from the origin point. So from this point, I need to measure what is this E1, and that is, if I have a field over here, what is this E1 and what is this E2? So in order to estimate that, I need to estimate the angular measurements. So now if I consider that this is along the phi equal to 0 degrees, that is, it is along the phi axis. So then if I assume that if I am measuring this angle, right, if I measure the angle between this x axis and the line what is considered, if I consider that this angle is 5 degrees, Then because of symmetry, you can observe that this angle is 5 degrees and even this angle is 5 degrees, because you can observe that this line is common between two and this line is common between two. And when I draw a line perpendicular to this angle will be 90 degrees. So now here the angle is 5, here the angle is 5. Now if I happen to measure the angular distance, if I happen to measure the angular distance, so I just consider, say this is 5, this is 5. I want to measure what is this distance. What is this distance? That is, what is the distance traveled by the wave if it is being generated? So what is the distance traveled by the wave from this point to this point? So if I happen to measure that, it is nothing but the distance measurement of this line what we are indicating. So if I happen to measure that line, what will be the value? It will be based on your Pythagoras theorem, based on your hypotenuse, this thing. So if I take cos phi is opposite upon your adjacent, opposite, hypotenuse upon your adjacent. So when we consider that, what we have this one given as d by 2 into cos phi, d by 2 into cos phi, the distance of this one. So similarly, the distance of this one is also d by 2, d by 2 into cos phi, into cos phi. So d by 2 upon this distance, d by 2 upon this distance gives you the cos phi parameter, that is hypotenuse upon the adjacent side gives you the cos phi. So therefore this side length will be d by 2 cos phi. That is what is specified over here, d by 2 cos phi for this one and this one. So if I take the overall measurement, if I take the overall measurement, if I just see here from source 1, if I move till source 2 with respect to this, if I move up to this point, what I'll be having is it will be equal to addition of these two, so which will be d cos phi. So this is the discussion pertaining to how these are obtained. So now when we are considering the field E1 and E2, we need to consider the distance in terms of radians, which is given by what? Beta into the distance parameter. Beta into the distance parameter. So here beta is nothing but 2 pi by lambda into the distance parameter. Now this is the distance in terms of radians. So in this discussion, we denote this one as dr. So which is giving you distance in terms of radians, which is equal to beta times d. Beta is 2 pi by lambda into d. So where d is the distance between source 1 and source 2. So this is your physical distance. This is the physical distance. And dr is the distance in terms of radians, which is given by beta times d. So this is this parameter will be useful for us in identifying E1 and E2. So first we got to know the distance between these two is d, which is the physical distance. The distance with respect to source is d by, that is with respect to the reference point is d by 2 and d by 2 for source 1 and source 2 respectively. And when I obtain the distance in terms of the hypotenuse and the adjacent side, it will be this part will be d by 2 cos phi and d by 2 cos phi. So what is actually this implying, we'll discuss in the coming forth discussions. So overall, when I measure, it is around d cos phi. And when I want to measure the field values, one important parameter which comes is distance in terms of radians, which is given by dr, which is beta times d. So these are the parameters what we need to consider. So now what we have is if we represent psi as dr cos phi, if we represent psi is equal to dr cos phi. then what is the total field with which we can make use of this equation in order to make the representation. So this is basically giving you the phase variation. It is giving you the phase variation. So now here what is the thing they have specified? They have specified that we have two isotropic point sources that is there. They have same amplitude and have same phase. They have same amplitude and same phase. So if I assume that the maximum amplitude emitted by this source is E naught, then in this case also it will be E naught. And if I have some representation of the phase with respect to both these sources, so both are in phase. Both are in phase. There is no phase difference between the two. But now what happens is, because we are considering at a distant point r from this reference point, we need to identify what is E1 and E2 with respect to this reference point. So in this case, if you just observe, what is happening is, if I consider, say, a wave which is been moving from this point, reference point. So if the electric field moves from this point to this point, so it is traveling some distance over here. Now this plane is perpendicular to this electric field. So let me consider in that form. So if I consider this, if you just check, say this is traveling, say, some amount of distance r. But because of the plane of observation, what happens is, the wave from source 2, if all start at same point, say at time t is equal to 0, so this will traverse a distance of r. And here what happens is, this will traverse a slightly lesser distance to reach this plane of observation. To reach this plane of observation. Similarly, if at time t is equal to 0, this starts, this will take little bit extra time to reach at this point. It will take, or it will traverse little bit more distance compared to this reference point what we are considering. So therefore what happens is, with respect to the observation point, the fields at the observation plane, with respect to this reference point, the field at the observation plane due to source 1 lags by some amount. It is lagging. And whereas the field due to source 2 will be leading, because if you start all at time t is equal to 0, source 2 wave will reach first, second this one, and third this one. Since this is the reference point, with respect to this I need to estimate. So because of that, source 1 is lagging with respect to the reference point, and source 2 field is leading with respect to the reference point. So E1 is lagging and E2 is leading. So how do I represent this? So this is represented with the help of psi, which is given by what? dr cos phi, where dr is what? Dr is beta times d. That is the distance in terms of radians. So as I specified, E1 is lagging with respect to the reference point, and E2 is leading with respect to the reference point over here. So E1 is field due to the source 1, and E2 is field due to the source 2. E2 is field due to the source 2 at the plane of observation. Now how do I represent it? So as we mentioned, dr is given by beta times d, and we assume that psi is equal to dr cos phi. So therefore, we need to estimate what is the total field at the distance er due to source 1 and source 2. Now it is nothing but the vector addition of these two fields, because electric field is anyways a vector quantity. The total field will be a vector quantity wherein we have to take the vector addition of these two. But in this one, what we do is the total field will be given as E is equal to E1 plus E2, where E1 is field due to source 1 and E2 is field due to source 2. Now, as I mentioned, as we specified, if I consider this point, E1 is lagging and E2 is leading. And since there is no phase difference between the source 1 and source 2, and they are having same amplitude, so then what happens is I can represent E1 as E naught into e raised to minus j psi by 2. So this is telling that with respect to the reference point, there is a phase lag of psi by 2 for source 1. Similarly, E2 can be represented as E naught into e raised to plus j psi by 2. So this plus psi by 2 is telling what? It is telling me that it is leading with respect to the reference point by psi by 2. So that is what we are having. So we have total field as the sum of the electric fields due to source 1 and source 2. And when we include the phase variations, we have E naught into e raised to minus j psi by 2 plus E naught into e raised to plus j psi by 2. And it is specified that the amplitudes of both E1 and E2 are same, and there is no phase difference. The only phase difference is present in the field due to the source point what we are considering, due to the reference point what we are considering. So now when we simplify this, so we take E naught common, it turns out to be what? E naught is common, it turns out to be e raised to minus j psi by 2 plus e raised to plus j psi by 2. Now we represent this in terms of sine and cosine. So what you do is you multiply and divide this equation by 2. So when I do this, what I'll be having? I'll be having 2 times E naught, and this one is what? It is the representation of cos psi by 2. E raised to minus j theta plus e raised to plus j theta divided by 2 is nothing but cos theta. So in this case, theta value is psi by 2. So therefore, what we are having, when we have two isotropic point sources, when we have an array of two isotropic point sources which have same amplitude and same phase, that is sometimes we refer it as in phase. So for this condition, what we have is the total field at this point. The total field at this point at a distance r is given by the cosine pattern. It is given by cosine pattern, but it will be referred to this equation, referring to this equation, wherein E is equal to 2 times E naught cos psi by 2. What is psi? Psi is equal to the radian distance into the angle what you are considering, that is the cos phi, cosine of the angle what you are considering. So therefore, if you just simplify this, it will be dr cos phi divided by 2. So this is the electric field due to two isotropic point sources which are having same amplitude and same phase or are in phase. Now, as I mentioned that these two are nothing but they are the vector quantities. So when we consider the vector quantities, we can represent even it in this form. So here, if I consider the reference point, which is a reference point, the field due to the source 1 is having a phase difference of psi by 2 with respect to the origin what we had considered, and the field due to the source 2 is having a phase lead of psi by 2. It's having a phase lead of psi by 2. Now, if I have to estimate the overall field due to this, what I do is I do the vector addition of these two. So this line, what I get is nothing but the total electric field due to source 1 and source 2 when I consider the source, when I consider the reference at the origin what we had seen above. So this E is nothing but this value. E is nothing but this value. So this is field due to the two isotropic point sources which are separated by a distance d between them and have same amplitude and same phase. Now if I want to normalize this, what I do is, say I'll consider this just for simplification. If I want to normalize this, what I do is I take this total field and divide it by its maximum value. So its maximum value is equal to what? You can just see it is 2 times E naught. This value will be fixed. Maximum value will be dependent on this value. So what is the maximum value of cos psi by 2? It is unity, that is 1. So when I consider that, Emax will be what? In this case, Emax will be 2 times E naught. And when I divide this equation by 2 times E naught, I get the normalized power pattern, field pattern, which is given by cos psi by 2. So 2 times E naught cos psi by 2 divided by 2 times E naught, which will be giving me cos psi by 2. And in sometimes what they do is they assume that 2 times E naught is equated to 1. 2 times E naught is equated to 1, which will be giving me the normalized representation in which we represent as E is equal to cos psi by 2. So sometimes we represent it in this form. So now here we observed the condition. So now if I assume that we equate 2 times E naught is equal to 1, the maximum possible value of 2 times E naught is 1. So then what happens is the equation reduces to E is equal to cos psi by 2, which is nothing but E is equal to cos dr cos phi by 2. That is dr cos phi divided by 2. So this will be the equation. Now here what we do is if I put in some substitute some values, that is if the distance is this much, what is the variation? So if I have say d is equal to lambda, what will be the value? If d is equal to lambda by 2, what will be the pattern? If d is equal to lambda by 4, what will be the pattern? So if I consider those conditions, then what I do is, so in this case what we have done is we have equated to 2 times E naught equal to 1, and next what we have done, we are considering say distance between the two sources is lambda by 2. That is distance between these two source points is lambda by 2. Now you got to know what is d equal to. D is given by lambda by 2. So if d is given, we can estimate dr, which is given by beta times d, which is given by how much? 2 pi by lambda, and d is lambda by 2. So this two parameters cancel, and dr, that is the radian distance in terms of radians, will be given as pi. So you are substituting d in this equation. You are substituting d is equal to lambda by 2. When you substitute d is equal to lambda by 2, in that dr will be equated to equal to pi. So that is what you are getting. So you got to know what is dr. So now if you substitute that value in this equation, 2 times E naught, I am just equating it to 1. And then dr, I got it as 5 when d is equal to lambda by 2. What I'll be getting is, I'll be getting the equation as E is equal to cos pi by 2 into cos phi. So it is dr cos phi divided by 2. Dr is how much? Dr is pi. Pi into cos phi, the whole divided by 2. So in this case, how do I obtain this pattern now? How do I obtain this pattern? So here what we can do is we can substitute different values of phi and try to see how the plot will be appearing. So in this case, what we are doing is, so this pattern what is represented, it is nothing but source 1 is here, source 2 is here. If the distance between these two is lambda by 2, we get that equation. And when we do the plot, right, the plot will be somewhat 8 shape. because here what we are considering, phi is equal to 0 degrees in this direction. So we'll be having a 8 shape distribution of the field for this given pattern, for this given condition. So how do I plot that? What you can do is you can substitute phi with different values and try to see what is the field value. And again, as I mentioned, don't go for ASTC rule. Just try to see what is the magnitude you are getting and try to utilize those values. So if phi is equal to 30, I am getting the field as 0.21. If 60, it is 0.7. If 90, it is 1. And if I still continue, so if it is say 120, what is the value? It will be around say zero point 0.7. If it is say 150, it will be around 0.21. I'm just considering the magnitude value. So if I keep on plotting, so these are the two sources. This is first source and this is second source. So with respect to phi equal to 0, what is the field? I am having no field value at this point. So when angle is 0, I don't have any field. But when angle is 30 degrees, I am having a value of 0.2. So yesterday we had seen a polar plot, right? You have a circle representation, if you remember. So that circle represents, say, the particular value. Say 0.2 is somewhere here. So that you can plot. So that is what you can consider. So when you plot these values, right? When you plot these values, you will get a 8 shape pattern for d equal to lambda by 2. So this is just an example. This is just an example what we are considering over here. So this is the actual field what we are having when two isotropic point sources are separated by a distance d and they are in phase and have same amplitude, which is given by 2 times E naught cos psi by 2, where psi is dr cos phi. And in that, one condition what we have looked out is if d is equal to lambda by 2, what will be the pattern? So similarly, try to see what is the pattern when d is equal to lambda by 4, lambda by 8, or lambda. So you can just check out with those patterns and try to see what is the result you are getting. So now the same condition in this one, what I did was I consider the reference point here and then I did the estimation of the total field at this point. Now, whether I'll get the same field when I do the when I change the reference point, I can just cross verify it. I'll leave it as an exercise for you. So what you can do is consider that this is the reference point. That is, reference point is at source 1, and try to identify what is the field at this point. So here again, the distance between these two is same d, and source 1 and source 2 are the two isotropic point sources. Both are having same amplitude and same phase. So in this case, the result will be same. Only one extra parameter what you'll be getting is you'll be getting a phase parameter over here. There is a total field, because what you're doing is you are changing that's the source, the reference point. You're changing the reference point. So that is only the minor change what you will be having over here. So when you do that, even that we have done it over here, when you simplify that, what happens is you will have this extra parameter which gives you the identification of the phase of the total field. Now this change occurs because you are changing the reference point. So previously reference point was in between. So with respect to that reference point, there was no phase difference. There was no phase observed over here. Phase was 0. But if I change the reference point with respect to this, what happens is you'll be having a phase of psi by 2. Okay. So that is what it indicates. So you can just try to identify the solution in the same manner. Try to identify what is the field at due to source 1, field due to source 2, add both, simplify the equation. You will end up having the solution as given in this equation. 2 times E naught cos psi by 2 into e raised to plus j psi by 2. Okay. So next, another point what we have to discuss is we have to identify what is the array factor for the given field. So previously for the given condition, we obtained that E is equal to 2 times E naught cos psi by 2. Now array factor is by definition what it specifies is it is the ratio of the electric field to its maximum value. Ratio of the electric field to its maximum value. This will give me the array factor. So it is indirectly giving me an indication that the electric field, how relative it is to the maximum field direction. So in simple form, it is the ratio of electric field for the given condition to its maximum value. So here, the what is the maximum value of 2 times E naught cos psi by 2? So if I just consider the maximum value of cos psi by 2 is 1, and this one will be equivalent to 2 times E naught. So therefore, E max will be 2 times E naught for this representation. So therefore, array factor is what? It is E divided by E max. So which is, you can consider over here, 2 times E naught cos psi by 2 divided by its maximum value, which is 2 times E naught. So therefore, array factor is given as cos psi by 2. Array factor is represented as cos psi by 2 for the first case what we have observed. So next we have slightly different condition. So based on this condition, you can again try to see how we can go ahead with the rest of the other cases. So next case, what we have two isotropic point sources which have same amplitude, but they are opposite in phase with respect to each other. So previously both were in phase, but now one is in total opposite phase. So if I consider, say, source 1, it is having same amplitude. It is having same amplitude. Both will be having a maximum, say, they both will be having a maximum amplitude of E naught. But when I consider the phase of 1 with respect to phase of 2, both will be having a phase difference of, say, they are opposite in phase. They'll be having a phase difference of 180 degrees or pi radians. There'll be a phase difference of pi radians. Now again, the geometrical analysis is same. So we have two sources, source 1 and source 2, which are separated by a distance of d between them. And if I consider this as the reference point, the distance of source 1 from the reference point is d by 2, and distance of source 2 from reference point is d by 2. And when I try to measure the angular variations, that is, if I assume that if I have a field at this point and if I move at a distance r, and on the observation plane, if I want to see with respect to this reference point, what is the total field? What is the total field? Then we need to estimate the phase variations which are present due to source 1 and source 2 and try to obtain the overall representation. So now here E1 is field due to source 1, E2 is field due to source 2. And these parameters we discussed again in the previous conditions. So again, I'll not be discussing this. So we have this distance as d by 2 cos 5. And if I measure this distance, it is d by 2 cos 5. Overall distance, if I measure, it is d cos phi. So wherein this is the phi what we are specifying. So this is phi equal to 0 degrees. Both the sources are assumed to be along phi equal to 0 degrees. So here again we are considering the reference point as the midway between these two. Now only condition what we have to check out is the opposite phase. So what is the representation of the opposite phase? So again here these parameters will be handy. That is dr is equal to beta d, which is given by 2 pi by lambda into d. So this is one thing. And next psi is, we assume that psi is equal to dr cos phi. Dr cos phi. Okay. So these two assumptions again, these two conditions will be referred going forth. So here what we have is Again, if I consider the reference point and at a distance r, the field E1, which is due to source 1, is lags with respect to this reference point, and E2 leads with respect to the reference point. That is, E2 is due to the source 2. So E1 is lagging, and E2 is leading. So if I'm considering the midway between these two, so that condition also remains same. So now what condition adds in is, so here we can observe. So E1 is given as E naught into E raised to minus j psi by 2. And here we have E2 as E naught into E raised to plus j psi by 2. But how do I identify the opposite phases? I have to identify the opposite phases. So in order to do that, what we refer is, we show the phase difference between these two with the angle representation, with the angular representation. So here, previous this thing, it was same, E naught into E raised to minus j psi by 2. This is due to the lagging effect of the field E1, and this one is telling that there is a phase difference with respect to the field due to source 2. That is, this condition what we have put forth, the sources are opposite in phase, that is opposite in the sense 180 degrees or pi radians out of phase. So if I assume that this is out of phase, then the angle of this one should be 0. So therefore the phase difference between these two sources will be pi radians, or they will be opposite in phase, or 180 degrees. So that is what this condition we are putting forth. So this phase is due to the phases or phase difference between the sources, that is source 1 and source 2. And this one is due to the consideration of the reference point. So now based on this, so we have E1 is equal to E naught E raised to minus j psi by 2 and angle pi. So this one we can write as what? You can write it as E raised to j pi. You can write it as E raised to j pi. And when I simplify it using the cis theta or cis equation, so cis pi when I take, that is cos plus I j, that is cos plus I sin theta, sin pi, cos pi plus I sin pi. So if I consider that cos pi is minus 1. So e raised to j is what? E raised to j is cos pi. Here it is plus. So it will be plus. So it will be I or j. It will be sin pi. Sin pi is 0. This one is minus 1. So therefore this equates to minus 1. This equates to minus 1. So when it is minus 1, I end up having E1 equal to minus E naught into E raised to minus j psi by 2. So now I have considered the phase difference over here. So when I'm representing the next one, no need to specify. So this one will be like 0. This one will be like 0. So if you want, you can equate this also. It is nothing but e raised to j 0. So what is cos 0 plus j sin 0? J sin 0. This is 0. This is plus 1. So this will equate to 1. So no need to worry about that condition now. So phase difference is already taken care in this parameter. So E2 is E naught into E raised to plus j psi by 2, and E1 is minus E naught into E raised to minus j psi by 2. So now what is the total electric field? Total electric field is given by sum of E1 and E2. So total electric field is obtained by E1 plus E2. Substitute E1 and E2, and when you're substituting it, you can observe what we are having. We have E naught common. We have E naught common. So when I take E naught common, what I am left is, I am left with plus E raised to plus j psi by 2, and I am left with minus E raised to minus j psi by 2. So I'll be left with this parameter. Now what I do is I'll represent this in terms of sign. So if I have to represent this in terms of sign, if you remember, e raised to jx minus e raised to minus jx divided by 2j gives you the sine x value. So that concept will apply over here. So we have a 2j value over here. So I'll multiply and divide this equation by 2j. And when I simplify this equation, what I'll be having is I'll be having the equation for total field, which is given by 2 times j e naught sine psi by 2. So previous condition I got cos psi by 2. Now what I'm getting, I'm getting sine psi by 2. So this is what we are obtaining. And what is psi? Psi is dr cos phi. If you substitute it in this equation, you have dr cos phi divided by 2. So this is the parameter what we are getting. Now what is the array factor what we have? So for this condition, so array factor is what? Array factor is E divided by E max. It is E divided by E max. What is the maximum value of this one? You take the magnitude of this. You observe that this sign parameter can have a maximum value of 1, and this one can have a maximum value of 2 times j into 2 naught. But when you consider that 2 times j into e naught, its value turns out to be 2 times e naught. So when I equate this, I'll be having an array factor of sine psi by 2. I'll be having an array factor of sine psi by 2. If you don't take the magnitude, you just estimate the maximum value. Maximum value will be equated to 2 times j into e naught. I'm not considering the magnitude. If I just consider this one, 2 times j e naught. So if I divide this equation by 2 times j e naught, what I'll be getting is I'll be getting sine psi by 2, which is sine dr cos phi divided by 2, which is the array factor. So here you can see that what they have done is, again, we are assuming that we are equating this one to 1. And when we consider that value, what we'll be having? We'll be having the field which is represented as sine psi by 2. So this is the value what I am having. Now again, if I consider d is equal to lambda by 2. If I assume that the distance between the two sources is lambda by 2, then how will the field appear? How will be the field appearing? If I want to observe that, what you do is, we know that d is equal to lambda by 2. So from that you estimate what is dr. Dr is beta times d. So which is 2 pi by lambda into lambda by 2, which simplifies to pi. So this one you substitute over here. So you have sine dr value is pi. So it will be pi into cos phi, this divided by 2. So you'll be having the field which is represented in this form, sine pi by 2 into cos phi. So now in this case, again, you can go for the representation in terms of substituting the value of phi and trying to obtain. So phi is equal to 0, what is the value? Phi is equal to 20 degrees, what is the value? Phi is equal to 30 degrees, what is the value? So if when you try to plot the field with respect to that, what you'll be having is you'll be having a pattern which is infinite shape like this. So in this case, what you'll be having is you'll be having one source over here and the other source over here. So with respect to that, you'll be having the pattern which is represented in this case. So you have, apart from substitution also, you have different method. That method we'll be discussing after we discuss, n array isotropic point sources. So in that, if I substitute n is equal to 2, I get these conditions. So there I'll be discussing these things. At present, I'll not discuss this. So this we'll discuss over there. So in simple form, in this case, what we are doing is, if phi is equal to 0, what is the value? Phi is equal to 10, what is the value? Phi is equal to 20, what is the value? If you try to plot it, right? So this is how the plot will be appearing. Okay.